scales resolves nicely. And so when we compare those two things, this the movie of the lung and this picture, you see a drastic difference in resolution. And as we will see, it's the same as difference in stability of methods. And the difference is not due to the fact that better mathematicians worked on this than on electrical impedance tomography. Actually, mathematics done on electrical impedance tomography is of extremely high level. But this is the fact of nature. We will try to understand why we have good resolution in some methods and why we don't have in some others. And although rigorous analysis might be difficult, in fact, it's pretty easy to learn how to tell the difference. And you can tell in advance that this thing is impossible and this is possible. And you can do this. We will learn how to do this, and then we will move from there to the role that hybrid methods play. I want to tell you in advance, I will show you some pictures that are, in terms of sharpness, are close to what we have here. Although I will not show real images, I will show only some simple phantoms. And if anyone shows you a picture like this and tells you, even like that, and tells you that it was done by electrical impedance tomography, you need to leave the room, since someone is lying to you. It's impossible. However, I will show you pictures that are obtained by hybrid methods, hybridizing electrical impedance with something else that are sharp. And so, but let's first start with what I want to discuss. I decided to compare these two pictures. By the way, as you were told in the previous lecture, those low resolution images still have a great value. For instance, one of the standard complications after surgery, especially in older people, is when the fluids get into their lungs. And it's usually hard to tell, especially in the beginning. However, as soon as you have some fluid in your lung, electrical conductivity will change drastically. And electrical impedance image will show it immediately. So you will not see sharp shape of this fluid. But you don't need to. You will know that it is there. This means that you have to start some active therapy. So there are, as you were told in the previous lecture correctly, there are places for very low resolution images as well. Okay, now I will go to what I promised, to some mathematics, since I promised some mathematics last time. Many people told me that it was a nice lecture last time, but there was nothing there. There was no mathematics. Now there will be some mathematics. And I already mentioned this, I just want to repeat that as we will see, all the tomographic methods eventually boils down mathematically to a problem of the kinds that you have seen, you saw just in the previous lecture. You have a PDE with, you know what kind of PDE, but you don't know the coefficients, and you have some measurements on the boundary, and you want to determine the coefficients. And we will see that all methods that I mentioned are underlined by such a problem, but the PDEs arising there are different. And we will learn how to tell immediately whether you expect low resolution or high resolution, and what it depends on. And we will do this kind of addressing in more details what does it mean to be stable, unstable, methods, etc. So that's what I already said last time and now. So I just repeat that we will have these examples of equations, transport type equations, elliptic equations that you already have seen electrical impedance tomography, you will see some hyperbolic equation problems. In all cases, the problem is that you know what kind of equation you expect. It's inside of a domain which you cannot penetrate. You need to find the coefficients, and everything you can measure should be done on the boundary. But the types of equations are different, and we will see that the results are different. I already went through CAT scan, so let me go to the last. So we finished figuring out that the X-ray tomography problem reduces to the following. You have an unknown function f of x on the plane or in the space, it doesn't matter. You can forget all machines, etc. And mathematically, problem both of X-ray CT boils down to the following. You have an unknown function f of x, and let's say it's in the planes, at least the commonly used CT scanners, they visualize a slice. And if you want to see 3D image, usually they put one slice on top of another. Nowadays there are already fully 3D machines, but let's say that we are in 2D case. This is the most common case. You have a known function f of x. It's essentially physically something like density of the tissue at the point x. So if you know this function, you can distinguish, for instance, bones from soft tissues. And mathematical problem is that your measurements, I will remind you some notations. You shoot a beam from the source with initial intensity. Intensity means how many photons per second are coming out of this. And you shoot this beam along the line L. Remember, you use collimator to make this a thin line. And then at the outcoming intensity is detected by the detector. So you have these two numbers. And we derived this formula, this Beer's law, and it essentially says that having these two numbers dividing and taking log, you determine the integral of this unknown function, which would be your tomogram, over this line L. And you already see that it's kind of a PDE thing. We developed some first order ODE. It was an ODE, we solved it, and that's how the Beer's law worked. But now let me start looking at this from PDE point of view. This is an ODE so far. So first I look at no-brain tomogram. It's not no-brainer tomogram. It is no-brainer, but it's the case when they take tomograph on someone like me who has no brain inside. So it's just nothing there. So, and I will introduce notations, and we will complicate this situation more and more. So what I'm looking at is the following. There is a function u of x omega, which I don't know, which means the following. In this volume, x is any location, and omega any unit vector that tells you the direction. And what is u of x omega? You have many particles swarming around here, not only the ones going straight in certain direction. There are plenty of photons here, and they move in different directions. So u of x omega tells you the density at this location x of particles that go exactly in the direction omega. And in our scanner, actually, what we did this. We only looked at this line and only in the particles along this line going in this direction. But actually, there are particles going in all directions. So, what can we say about this? Let me take directional. What is written here is the directional derivative. I didn't plan to push this button, but I did. So what is written here is the directional derivative of this function at the point x in the direction of this vector omega, in the derivative in the direction in which the particle is moving. So in other words, I want to see how the density of those particles, they all move in this direction, and I look only along this direction, how the density of those particles changes. But I remind you, it's no brain problem. There is nothing there. So nothing happens to the particles. They don't get absorbed. They don't get scattered. Nothing happens. They are not produced by anything. It's empty. That's why my friends told me that you shouldn't worry when they checked me for a brain tumor, that you cannot possibly have brain tumor. You're missing some necessary conditions of that. So this is what is written here, that this directional derivative is zero. If it's empty space, nothing changes. This density of particles moving in the direction omega, if you differentiate in direction omega, zero derivative. So no brain. And the conclusion would be that if this is where you shoot your particles from, and this is where you detect them, what you can say about the incoming and outcoming intensities, they are the same. So that's the simplest. What you have, I just wrote here as a PDE what we did as an ODE for Beer's law. We took into account that the locations are not only along this line, there are other locations that we haven't studied, haven't touched yet, that there are particles that might be particles that move in different directions. But this is exactly what Beer's law says, that along this line, there is no obstacle, no scatterer, nothing that influences those particles. Now let's look at, I don't remember whether I told you what RT means, but it says here, radiative transfer equation. And we will gradually approach this equation. So now, no brain tomogram is no brainer, so you don't need to do it. It's cheap to know that nothing happens there. But what if there is attenuation? What does it mean attenuation? At each point, certain portion of photons get lost, absorbed. For instance, absorbed by bone, absorbed by other tissues. So at each point, there is a certain number that tells you that this portion of incoming particles at this point is lost. So again, the notations, U of x omega is the same thing. F of x is the attenuation coefficient, which means that at point x, this portion of particles get lost. By the way, notice that attenuation doesn't depend on the direction. Usually, if it's something like density, it cannot tell from which direction the particle comes. So it's isotropic situation, in other words. This attenuation is isotropic. If the particle comes, it gets absorbed or not absorbed, irrelevant of what was the direction it was coming from. And this is the most common thing. It's not whole story. There are anisotropic cases, but we deal with the isotropic. And this is exactly the case of X-ray CT. So let's look how PDE looks like now. This is a new PDE. Let me explain what happens. This is just a simple balance equation. So if there were no attenuation, this term would give you zero, like we did before. But now, certain portion of this number of particles get lost. And what is the portion? This is the portion. So what is this? It's just balance equation. That you account for what is lost, the sum should be still zero. This is, again, it pretends to be a PDE, but it's actually an ODE. It's just first order ODE along this line. And this is exactly the ODE we solved to get the Beer's law. And when we do this, we get this, that outcoming intensity is incoming intensity times e to the power minus integral. Integral over omega means integral over this line in the direction of omega. So this is, you see, equation gets more complicated. We will eventually assemble the full-blown radiated transfer equation. And nice way to think about this is the following. It helps when you understand other methods. what is the meaning of this coefficient? So you send certain number of photons in, that's how many get out. This means that this is essentially up to some normalization. It's just probability of a photon that you shoot in director of omega to get through the whole body and to reach the detector. That's what it is. So those photons get out with this probability. So this is the portion of photons that get out. So this is, we have a more complicated equation. Now we account for attenuation. And this equation, this is already a PDE, not an ODE. Although it's still an ODE. Truthfully, it's just along characteristic lines, it's just ODE, which we solved before. So far it's all ODEs, but the way it's written is still a PDE. And the picture of the knee that I showed you shows that it's pretty stable. CT scan, and if you ever have seen other CT scan pictures, they're very sharp, which means that small errors don't influence the picture much, and that's what we call stable. Well, the truth of the matter is all of those things are unstable. Whereas the previous lecture explained instability is that what we are trying to do, we are trying to invert compact operator, which never works well. But this applies to all tomographic techniques, to CT scan and to EIT. But you saw that, so they're all unstable, but you saw that the instability is quite different. In CT scanner, you can beat this instability and get pretty good resolution. In EIT or optical tomography, as we will see, you cannot do this. But this is pretty stable. So what I want to do, I want to eventually collect all those PDEs underlying our methods to see which ones produce stable reconstructions, high resolution, and which ones do not, and then we'll understand why. Actually, it's very easy to understand why, and it's very easy to apply, although not that easy to prove. But who cares about proofs? It's medical diagnostics after all. So, this transform from function f of points to a function of lines. So you take function of points and integrate over all lines, you get function of lines. It's Redon transform. And again, as I said before, every name attached to a research result is wrong name, since someone did this before. Actually, it's nice. It's so-called Arnold's principle. It's nice. It has nice history. Vladimir Arnold, who probably many of you know his books, etc., he was a great mathematician. He once wrote to great physicist Michael Berry that what was called Berry's phase, that's a very nice object in physics, actually had been known to Russian people who working in optics long before, and he sent the references. And Berry replied formulating Arnold's principle that every name attached to the result is the wrong name, but he also drew a corollary. Arnold's principle applies to itself. Okay, so I don't know whether I will need it. I will probably skip by now. I just will show you that's how what is called sinogram looks like. That's a picture not in coordinates of points, it's in coordinates of lines. It's so-called normal coordinates, the directional vector which is perpendicular to the line, and distance to the origin. So this is distance to the origin, this is, or the other way around, this is a vector. And you see it's called sinogram since it's a union of sine curve. And why is that? Just imagine that you take a tomogram of a single point, a very tiny object. And when we figure out what it is, it's a very simple geometric problem. You will see why you have sine curves. But I will not need this. Now there is another technique I already mentioned before, SPECT. single photon emission computed tomography when you give to the patient radionuclide, and it shines from inside. You detect this shining outside, and you need to find where the sources are. Now let's see what is the PDE underlying this problem. Now we have another term, sources. So if you have sources that produce new particles, the balance equation will be like this. So this is just change in the number of particles, and change can be due to what? Due to them get absorbed, and we accounted already here by attenuation, and they can be also produced. Now this is also an ODE. It pretends to be a PDE, but it's still an ODE along this line. You can solve it. Unlike in Beer's law, it's inhomogeneous ODE. First order inhomogeneous ODE, you solve it, and you get the formula. By the way, again, this is equation, so I forget to say what I should say every time in all those examples. So the problem is you have this underlying PDE. Now you have two unknown two functions, f and s, and let's say you already know f. You found it from X-ray CT. Now you need to find s. And what you know, you only have boundary measurements. You shoot something, and you measure what comes out. No access to the interior. This is, again, inverse coefficient problem for a PDE. Again, this spec is very stable. Spec pictures can be almost as good as CT's picture. And you can write it, what I did, I wrote it as a PDE problem, inverse PDE problem, but you can write it in inverse transform, random transform type formula. Let me explain what it is. It's just solving this non-inhomogeneous ODE, but the meaning is the following. So here is your detector. Now the sources are here inside. So you have source at the location x of intensity. Oh, it should be not f of x. I changed notations on the fly. That's what we do when you cut and paste from different things. It should be s of x. So in the intensity of the source. So this source produces uniformly in all directions s of x particles per unit of time. But not all particles that it produces in this direction get to the detector. How many get lost? Let's call this Lx. But we already know the answer. You remember the probability for a photon emitted here to reach here is the integral e to the power minus integral of attenuation over this portion. So you emitted f of x photons, or s of x photons, that's the intensity of the source, but each photon has this probability to survive the detection. But now you have to add, sources can be everywhere along this line. You need to integrate over it. And so you have transform of Redon type, which actually looks much more complicated, but I screwed up notation. This f of x should be s of x, and this mu should be f. But you know that the one definition of mathematician is that someone who says A writes B, thinks C, but actually it should have been D. That's in these terms I'm a mathematician. I do this all the time. This is kind of a little bit complicated transform of a function with a functional parameter, which is also kind of enters in complicated way. It's pretty complicated transform. It's a weighted Redon transform. You integrate your function over lines, but then with some pretty complicated weight with the functional parameter. Well, for a long time it was considered to be impossible to invert it explicitly. Why? Not since people tried and failed. Since every sane person looking at this transformation, which has, let's look at this as a transform of function f with this weight. And this weight has an arbitrary functional parameter mu. No insane mind would believe that there should be explicit inversion formula. So no one tried, since it was clear to everyone, including me, that it's insane to try to invert it. But there were two younger guys who were uneducated. They didn't know it was impossible, they just inverted. It was around 2000. The thing was around in 70s. But how they inverted it? What I want to say is that if you try to invert this thing, looking at it, it will not work. First of all, it doesn't have any symmetries that random transform does. It's bad transform with arbitrary functional parameters that enters in some ridiculous way. However, they didn't do this. They looked at the transport equation. And they worked with the equation, not with the transform. And that's what solved the problem. The equation is more important. There is also PET, positron emission tomography. I already mentioned it before, where you have a source which shoots simultaneous pairs of photons in both directions, and you put, if you have two opposite detectors detecting simultaneously, this means there was something on this line. It is actually better thing than SPECT mathematically. And since, look, you emit two particles, probability that this particle reaches this detector is this probability, right? E to the power minus integral over this is L1x. We just discussed this fact. But probability for the other photon to reach the other detector is this one, where L2x is this one. And these events are independent. So probability that both of them will be detected is the product of those. But now look, marvelous thing happens. When you multiply those probabilities, you get something that doesn't depend on x. And you get integral transform that looks like this. And you see, unlike in the SPECT, where this integral was not over the whole beam, but only a portion of the beam starting at the point x, this doesn't depend on x. You can pull it out. You can pull it out. And then look what you have. You have standard random transform and a function that you, hopefully you know. If you know the attenuation and you know shape of the body, you know this function. So essentially PET mathematically is kind of equivalent to the one of x raised to t. It's much better than SPECT. It's much simpler. It doesn't say, you see equivalent in quotation marks, since it's not exactly true. People who have worked on PET, there are many physical and technical issues that arise, and it's not as nice as mathematicians are saying, but still, it's stable. Now, what we have noticed so far, that those, in all previous techniques, you have 2 points of view. Either you have integral transformation that you want to invert. It's radon or attenuated radon with this weird weight. By the way, knowing inversion formula is neither necessary nor sufficient for making a machine. People have been using SPECT machines for generation, and they did pretty good job reconstructing the images. On the other hand, without knowing formula, everyone believes that there is no formula. So there are ways to do this numerically very well, which I will not be able to discuss here, but it also has nice mathematics without knowing the inversion formula. On the other hand, since 2000, when the inversion formulas were found, there was no improvement due to the quality of reconstruction. Inversion formulas so far haven't succeeded in beating the performance of machines that didn't know any formula. So in applied math has different mindset. So having an inversion formula is neither necessary nor sufficient. But what I want to say is that we have two points of view. One is integral transforms, and another underlying PDE. So in other words, what are those integral transforms? They're not fundamental. They just traces on the boundaries that we see from something that's going on inside. So I would want to say that these random transforms, they're merely reflections or even shadows or ghosts of a deeper mathematical object, this radiative transfer equation inside. And there are occasions when you cannot do much with this integral transform, but you can do a lot if you look at PDEs. And about those ghosts, I just wanted to recall how Bishop Berkeley, when the calculus was developing, he called infinitesimals the ghosts of departed quantities. So our random transforms are the ghosts of departed PDEs. And this equation, or as we will see, this equation RTE also handles optical tomography. So let's, and by the way, again, I need to mention Chandrasekhar. He had a fundamental monograph on studying. He didn't do inverse problems, but he did a lot of study of this equation. However, this is not everything that could and should be included. You know, what can happen to the particles flying? They can be absorbed, attenuation accounted for them. They can be born, sources counted for this. But none of those change the direction of the flight of the particle. That's why all those PDEs actually were ODEs, and they were easy to solve. However, we know that particles can scatter. And so we need to add additional term. This is a scattering term. And it might look complicated, but actually it's a very simple thing. So we are counting particles moving in the direction of omega. But you can get particle in this direction that came from a different direction, omega prime, and scattered into this one. So what you have particles that came from the direction omega prime, then some portion of them, that scattering amplitude, that's the portion of those who scattered from omega prime to omega. So these are the new particles in the direction omega that formerly were moving in the direction omega prime, and you need to integrate over the unit circle of directions omega prime. This is scattering term. What is absolutely new now is that it's not an ODE anymore. Since we now mixed up in all previous considerations, omega was fixed and you shouldn't care about other values of omega primes. Now they all mix together. And this is the equation that handles optical tomography. When you send scattering actually is present even in X-ray CT, but it's usually ignored. It's ignored in two ways. The particles that get lost since they scattered away, you just include this into attenuation coefficient f of x. So f of x now accounts not only for particles absorbed and dead, but those that scattered away and we don't observe them anymore. However, there are reasons which I don't want to discuss, by which it is more or less innocent thing to drop this term in X-ray CT. It's not innocent at all in optical tomography. What do you do in optical tomography? Again, you send something, but now you send light photons. And photons, if you go deeper than like a millimeter, they start scattering like hell. They scatter many, many times. And there is this experiment that I will show you. So I don't know whether you see the light coming through my finger. Do you see it? You can do this. be careful. You can do this with red laser. I wouldn't do it with some others, especially if you go to a lab to use the laser. Use red laser pointer. So what it shows that the light actually goes through my finger, but there is one strange thing. We all know that there is a bond there, but no matter how hard you look, you will not see any trace of the bond. Since what happens is that this term, the scattering, photons scatter at this distance. They already scatter so many times. They completely lose memory about where they used to be. So the memory about any internal locations is lost. That's why you don't see the bond, which is definitely there. And this is the reason. And again, this is already the full equation, and studied by Chandrasekhar. And optical tomography is a terribly unstable, low-resolution method. It's a very valuable method since, for instance, tumors are several times darker than healthy cells. But you see, and talking about small tumor, you cannot see the bone there. So it's very important modality. It's cheap and safe and everything else, except that it doesn't have any resolution at all. And it's strange. Look, the underlying equation is almost the same as before. And we had stable reconstruction. Now we lost any stability. So let's look. There are other transforms of random type, integral type. I will not be dealing with them. I just mentioned them. There are other transforms of random time when the data you measure is integrals of a function over something. Curves, lines, planes, surfaces. For instance, the spherical mean operator, when you measure integrals of a function over circles centered at your detectors. You have heard about this series of lectures by Bartzonia. This arises in thermoacoustic tomography. An interesting transform is transform over cones. When you get integrals of your function over cones, it's very over-determined transform, and since there are very many cones, you count dimension of number of cones, and it's much higher than dimension of your space. And this arises in so-called Compton camera imaging. I will not be talking about this. If anyone is interested, I tell you privately what it is. You can have even non-Euclidean versions of random transform. And on hyperbolic plane, probably some of you know that there are two analogs of lines, geodesics and horocycles. And you can have two types of random. And you might think, why do you need it? Well, it arises in electrical impedance imaging. It's funny that in electrical impedance imaging, it's not linear problem, but when you linearize it, you will see that there are this composition of two operators. One of them is just random transform, except that it's non-Euclidean, it's hyperbolic. And another is just convolution, explicitly written convolution. So it seems that EIT should be less like a piece of cake. People have done inversion of those transform on hyperbolic plane both analytically and numerically. It works as centered random. And the other part you need to do, you don't need to deconvolve. And this is the killer. This is the killer. This deconvolution, it's like deblurring. For instance, imagine that you convolve a function with a Gaussian and then you try to deconvolve. I wish you good luck. So that's what happens. But it's funny that non-Euclidean geometry, hyperbolic geometry arises in electrical impedance tomography. It's just not that surprising. Since I believe there are some engineers here, but there are curves of two types. circles tangent to the boundary and circles orthogonal to the boundary. These are correspondingly horocycles and geodesics. But probably if you have dealt with electromagnetics, you should recognize potential lines and current lines. If you run currents through this. So there is a reason why it's hyperbolic geometry, but it doesn't help. It doesn't help anyway. There are weighted Redon transforms. For instance, Professor Bowman was talking about them, and I also mentioned in spec those weighted transform. There are generalizations to Riemannian manifolds and non-Riemannian manifolds to whatnot, and for instance, you heard about this in Korolev's lectures. But again, to understand the issues of why some tomographic methods are stable, why are not, it's much better to look not on integral versions, but on PDE versions. And so that's what I will do. So now I will show you the problems that simultaneously models optical tomography and electrical impedance tomography. So you have this equation, and in electrical impedance tomography, this mu is 0, it's not there. U is potential, sigma is the conductivity, and sigma you want to find. In optical tomography, this mu is what so-called absorption coefficient. It shows how much light is absorbed, and this, instead of sigma, it's so-called diffusion coefficient. And you want to find both. In both cases, this equation lives inside of your domain, and all measurements you can do, you're allowed to do, are on the boundary. For instance, this Dirichlet Neumann or Neumann to Dirichlet maps that you just heard about. Well, it's terribly unstable. By the way, I said about optics that I showed you first order PDE model RTE equation for optical tomography. Now I say that this second order elliptic equation, what's wrong with me? The thing is that it depends on if your photons, if you look, for instance, at lesions or blood vessels or tumors, skin depth, you can neglect scatter. If you go like several millimeters deep, you already have a lot of scatter, you have to do RT. If you go deeper than, let's say, centimeter, then there is so much scattering that the so-called diffuse model is used. And instead of RT, if you go deep enough, for optics you use this second order elliptic equation. So they have very much common, very much alike, electrical impedance and optical tomography in terms of recovering coefficients of this equation. The only difference is that you use different boundary data. And in optics, you have this extra coefficient which you don't have in electromagnetic. Well, they both are terribly unstable. But you see, something has happened. This equation does look different from RT. But there are other methods that lead to still different PDEs. And this is the first hybrid method, this is the best developed hybrid method, or coupled physics method. And I will tell you briefly what it is and just show a PDE model. We will return to it later. And so what is the idea of hybrid method? The idea is to try to combine different physical techniques of scanning, different types of waves to produce better reconstruction results. Combination can be done on 3 different levels. So what you do, you first of all do something physically. You send waves, something happens, you measure something. Then the second step is you apply some inversion algorithm. You get the picture. And then you do something with pictures. And you can make hybrid methods on each of those levels. Let me go backwards. For instance, if you have two scans, one, let's say, is PET scan, and another is X-ray scan. You did them completely independently on different machines. You have two pictures, but you know that these are pictures of the same thing. They show different features, but of the same thing. So sometimes it's useful to put one onto another. You have to be careful to place them properly. It's so-called registration problem, which solves a mathematical problem. So you place one on top of another. Sometimes it provides more information for you visually. But this is not what I will call hybrid. Another type could be that you run one scan and another, you don't produce pictures, but you take data from both scans and try to use them in algorithms that uses both. For instance, I told you about spectra. In spectra, there are two unknown functions. There are attenuation, but you don't care about attenuation. You're interested in sources distribution. So what you can do CT scan. You get attenuation. And then you take spectra data and you use this knowledge of attenuation to recover the sources. So you combine on the level of algorithms. You just take two sets of data and try to use both. But what I will be talking about is what probably is called coupled physics, where you combine them on the level of physics. In other words, when one type of wave either modulates or maybe triggers completely different type of waves. So they interact physically. And you know what? Alexander Graham Bell found an effect that relates sound and for instance, light. And this is what started being used since it had to wait for 100 years till it became useful. So what is the idea of thermoacoustic tomography? The idea of thermoacoustic tomography is the following. Imagine that I send like breast imaging, for instance. I send microwaves, or maybe I send laser light. They have fantastic contrast. If there is a tumor there, the response will be like 5 times stronger from the tumor than from healthy cells. It's fantastic. Well, if you send photons, you know you have no resolution whatsoever. If you send microwaves, or even worse, radio waves, which is done, radio waves are so long that you will be able to detect the tumor when it will be the size of your car. So these two things, they have fantastic contrast. They have no resolution. Now let's look at ultrasound. I told you it has sub-millimeter resolution, but it has no contrast. What if we combine those? How can you do this? If you do this as follows. I turned it off. So here is the cartoon of thermophotoacoustic tomography. The words thermo and photo, they distinguish what is a triggering signal, whether you send microwave or radio wave or laser beam. But the rest mathematically is the same. So what you do, you send very broad electromagnetic pulse through the object. It could be broadened laser beam, it could be microwaves, it could be even radio wave. It goes through the tissue, and what it does, you see, little bit of energy of this beam is absorbed everywhere. In other words, you heat up the tissue. And this heating up should be negligible. You don't want to cool the patient. But the changes in temperature are so minimal that the patient doesn't feel anything. But it does happen. So is absorbed throughout the tissue. And if you call f of x the portion of energy absorbed at the point x, if you use this function, you would have your tomogram. Wherever it's high, it's tumor. Tumor absorbs 5 times more energy in microwave region or in optical region than healthy cells. You're done. You see peak, it's tumor. Well, but you need to see this peak. So there is this hidden function f of x, which you don't know, and you want to know. What is this function? What does it do? And here the thermoacoustic effect kicks in. That since energy is absorbed, you have heating. Whenever you heat something, it expands. Therefore, what you did, you created a pressure wave here. Resources everywhere. And where are the stronger sources? Where the tumors are. You absorb more energy, you proportionally create a stronger pressure wave there. So now, but if you have this pressure wave, it's actually a sound. And in technical implementation, it's ultrasound. What you do, you put microphones, there are transducers around, and you listen to this sound. That's why, if you remember in the beginning, I used this nice title, Can You Hear the Heat of the Body? And you can. So what you do, you use ultrasound transducers to detect this pressure wave around. Then you use ultrasound reconstruction, which will give you, I will give you a mathematical model. From this data collected, you try to figure out what were the sources, what was the initial pressure wave. And where it's high, it's tumor. So you did hear the heat of the body. And that's essentially the same thing. So you put, it just introduces notation. So you have what I call observation surface. You put your transducer along the surface, and essentially, it's not exactly true. But essentially, you deal with kind of random type transform. Since what does your transducer hear at this point at certain moment? It hears the signal from all points at the same distance. So essentially what you have spherical integrals of your node function, f. And that's spherical, or circular random transform, which you heard about from Bartsumian. But it's not the whole truth. It's not the whole truth. Indeed, it's not exactly what you measure. What you measure exactly, we will see on the next slide. And it will be not integral transforms, it will be PDEs. Besides, even this were true, if this were true, if your medium is acoustically inhomogeneous, if sound speed is non-constant, you won't have any spheres here. You have God knows what. All your integral random transform mathematics falls apart. But what is the truth? I already said all of those words. The truth is the following. So you have a pressure wave, pressure P of xt. X is location, T is time. So you have a known function P of xt, where X is location, T is time. It's the strength of your pressure wave. It satisfies the standard wave equation where C of X is sound speed, which could be variable. In breast imaging, it's not that variable, maybe up to 10%, but usually it's not very safe assumption that it's constant. So you have wave equation, and you have initial conditions. So these are initial conditions that you started with. This f of x you don't know. As the second condition I will not explain, but it holds in the setup that is used. And what do you measure? You measure the value of your pressure where? On your observation surface. So here is the picture. If this is the time line, and this is the space, you have this cylinder, this is observation surface, and this is the time variable. So what you have, your function at P of xt, you measure on side walls of this cylinder. And what you want to know, you want to discover, you want to recover the initial condition. It looks ridiculous. Indeed, it shouldn't be possible. Every PDE textbook teaches you that apparently what we try to do, we try to recover initial conditions from boundary conditions. But it's more or less up to some fitting conditions here. You can more or less prescribe any boundary condition and any initial condition, and there is a solution. So, boundary condition and initial conditions look completely independent. So it's kind of stupid thing to try to do. But the truth of the matter is that what I said is an illusion. It's true if you have wave only in the cylinder. If you have boundary value problem, there is no actual physical boundary here. That's where we listen only. It's observation surface. Wave actually is free to go further to the big world. There is no physical boundary. This S is not, and actually technically it's done in such ways that you don't disturb pressure as much as possible. So the wave is not in the cylinder, it's in the whole space. You observe it here. And then analysis shows that then you're okay. Then you're okay. It is stable. Now look, it's again a problem of you do measurements on the boundary and you want to find something inside. In this case, this initial value inside. And it is stable. And now we are dealing with hyperbolic equation. In ultrasound, you also have deal with, that's a model of ultrasound. So you have again pressure wave. What you do, you place your source at certain point x naught outside of the body. You create a source there. Then it creates again pressure wave, and you measure the response at some other point, x1. So at x naught you have your source transducer, and x1 you have transducers that measure the response, and you can move those around. And this is the data you have. And you need to find this coefficient, speed of sound, COX. That's what ultrasound. And if there are some caveats here, but if it's done properly, it's stable. So you see, we have, I will finish just combining the information that we got. We looked at several major problems, imaging problems, X-ray CTs, 2 emission type problems, ultrasound, optical tomography, electroimpedance tomography. They are all unstable. But they are all have underlying PDE whose coefficients I want to find. Some of them happen to be pretty stable. Some of them happen to be awfully unstable. So what's going on? Surprisingly, there is a very simple answer to this, and you will have this answer next time. We will be able just to look at this and say, oh, this should be fine. It doesn't mean that you know how to do this, but you will understand that, okay, this method should give me good resolution. If I don't get it, I'm stupid. And this method shouldn't give me. So if I don't get it, it doesn't mean anything bad about me. So.